Okay, so it's time now to continue with our review for the Unit 4 exam. And now we're going to be talking about gravity, which is going to be lesson number 8. So in your textbook, this is going to be chapter 8, sections 5 and 6, chapter 9, sections 1 through 4, and section 6, and then chapter 10, sections 2 through 7. So first, you've got to know what is the formula for the force of gravity. So we'll write that down here, that the force of gravity is going to be equal to a negative. Now, you normally, when you're calculating with it, you don't need to include the negative sign in there. It just means that gravity always attracts. And then it's got this constant on there called big G, which is the fundamental constant of the universe, which goes with gravity. You can ignore it, so that's not going to be on the exam. But the important thing is that you're going to have any mass 1 in the universe is going to be pulling on any other mass in the universe. So that you got mass number 1 and then you got mass number 2. So your head could be mass number 1, and then the Earth could be mass number 2. But also, this could be mass number 1, and your head could be mass number 2, and there is a force of attraction for that object to your head because of the force of gravity. And then it also is going to be divided by the distance between those two objects squared. So you should be able to do a problem such as this. If two objects get 4 times further away from each other, what's going to happen to the force of gravity? So don't say that the force of gravity is going to get 4 times weaker, because remember, you've got to square it. So 4 times 4 is going to be 16. So you would say it gets 16 times weaker, or you could say that it's 1/16 as strong. Okay, then you should also be able to explain, so this would be a good essay question, why do things look weightless in outer space? Okay, and it's because everything is falling at the same rate. So that if you're in outer space and you're close to the Earth, you're going to be pulled towards the Earth. So you're actually falling to the Earth. But let's say that you've got an object in your hand and you drop it. Well, that thing is going to look like it's suspended in front of your face, but you're falling at a certain rate towards the Earth, and this is falling at the same rate towards the Earth. So therefore, it looks like it's just kind of floating around in front of your head. But in fact, everything is falling towards something else because of the force of gravity. So then this brings up the second idea, is that if the people in the International Space Station are falling towards the Earth, why don't they crash into the Earth? And it has to do with that they are, as they are falling, they're also moving sideways at the same time. So that by the time they fall the distance towards the surface of the Earth, they have orbited over to another position. So it's like they're starting over again. And so you should be able to explain that on the exam. Okay, then we talked about what was the gravitational field. So you should be able to draw the gravitational field of the Earth. And the way that you're going to do that is that if you have a mass here, then pretend that you got a teeny tiny little mass and you drop it. What direction does it go? So it's going to go in that direction, but if you dropped it from over here, it would go in this direction. So you would end up with something that would look like spokes on a wheel. And then that would represent the gravitational field of the Earth. But remember, that would be a two-dimensional picture for what the gravitational field would look like. So in actuality, it's more like a pin cushion. So could you imagine that there could be a pin that is perpendicular in this direction here, and then you could have another pin on the opposite side. So imagine a pin cushion, and you're putting pins in all different directions into the pin cushion. So that would really represent the gravitational field. Okay, and then we talked about the gravitational potential energy. And so the actual formula for the gravitational potential energy is the top one. So equation 8.3. So you see that it depends on mass number 1 and mass number 2 and the distance between them. And so depending on the distance and the masses, they're going to have a certain amount of potential energy in that configuration. Now, when you are close to the Earth's surface, however, equation 8.3 becomes this equation up here. Now, you still have the mass of one of the objects, and you still have the distance between them. But the difference is that the mass of the other object is contained in this g thing. So that g thing is the 9.8 meters per second squared thing. And so that is an approximation for the gravitational field at the surface of the Earth. So that the top equation, equation 8.3, becomes equation 6.1 when you're very close to the Earth's surface. And also, the force of gravity can be approximated. So here is the official force of gravity that acts on mass number 1 caused by mass number 2. But we could also approximate this thing, so approximately it is going to be the same as minus m, and so this m here could be mass number 1, but then the g thing is the combination of all of this other stuff. When you put in the radius of the Earth and you put in the mass of the Earth and then you do your calculations, all of this other stuff becomes g, that 9.8 thing. So you're left with the other m, which was this m here. And then the gravitational field, big G, which is true for anywhere, can be approximated by little g when you're on the surface of the Earth. And then the third one is saying that the potential energy can be approximated by this formula up here. So on the exam, you're not going to be doing anything with this formula here. Okay, but you will be asked questions about the gravitational force. Okay, and then you should also be able to calculate the force of gravity, which is your weight, when you multiply your mass times 9.8. And then you should also be able to calculate potential energy using this formula down here. All right, let's take a break. When we come back, we will talk about orbital mechanics.